Yep, countdown. So we're talking about convolutions today. Yay!
What is convolution?
And convolutions are very involved and convoluted, which might be why we get that same word there. So convolutions are one of the most powerful and one of the most annoying things in differential equations. Whenever I think about a convolution, I have to always stop and look at it for a while before I understand what the heck is going on. In my analysis class in graduate school, we did convolutions all the time, and every time I wanted to gag. That's not to say that what we'll be doing will be terribly difficult. And a lot of the convolutions that we'll be dealing with in this class are either not bad, or you're going to write it in the form of your answer. So your answer will be t convoluted with sine. Done. You won't actually calculate. Some of these you will calculate, some of these you will not. For example, I do not want to see you convolving sine and cosine together. That is disgusting. But today we're going to talk about convolutions. This is the last section that will be on the common exam. This will be on the common exam. And this fills in the last true topic for Laplace transforms. It solves a little niche that you didn't know you had. Yep. Now, so far, we've been dealing with these, and we solve for our y of s. We get an h of s, and you see 1 over s squared times s squared plus 1, and you think, okay, how do you do partial fraction decomposition? That's possible, but in some cases it's not. In some cases it just becomes so ridiculously redundant. It's like, why? Is there another way? The answer is yes. And this particularly happens when we have inside of our y of s 2 or more factors that multiply together, although you don't want to have more than 2. One convolution is enough. So I have 1 over s squared and 1 over s squared plus 1. It would make sense because I know what this is, right? 1 over s squared, if I do the inverse, it's just t to the 1. And then this is pretty easy. This is just sine of t. And so our question is this true? If I have 2 fractions being multiplied together, we hope and we pray that I can take the inverse of this and the inverse of this, and so this is just t sine t. That would be nice. That would be really nice.
It doesn't happen.
It doesn't happen. Woo! Yep. So, we're going to be talking about how this equality doesn't actually hold, and it's actually multiplication in Laplace space becomes a special kind of multiplication or a general case in real space.
And yes, that's what convolution is.
Exactly. Ooh. So that special kind of multiplication is sort of like a multiplication inside of an integral. So, your book has the proof behind why it's true. None of you are interested, I can tell you now. But if you are, there is a proof in the book. It's actually very, very straightforward. But you're going to be more interested in solving these than the proof-based stuff. But for those of you, and there might be one or two of you in here who are interested in the theory, it's there and it's very straightforward. But for everybody else, I'm skipping it just for you. So, let's actually show this, and here's an example of why it doesn't work. If I have 1 over 1 and sine of t being my 2 functions in real space, when I take the 2 Laplace transforms, I get 1 over s and 1 over s squared plus 1. And so it would make sense in my one weird world that if I multiplied inside the Laplace transform, it would hold. But it doesn't. So, we don't have an equality. And yes, I know that's supposed to be an S and not an S. Is that what you're going to say?
Is it uncultured because Laplace transform are linear operators?
If we linear operators mean if we add, it's okay. And Laplace operators are okay in that way. But we say that they don't commute. That means A times B isn't necessarily the same as B times A. There's all sorts of things. Huh? Non-commutative? It's also not abelian. Non-abelian. I'm sure there is a word. What?
Yeah.
I don't remember the name. I'm sure there is a name, but I'm pretty sure abelian is when you can switch back and forth, and it's non-abelian if you can. That's the word that's jumping in my head. It's named after the Norwegian mathematician. He was a contemporary of Nobel. He's also the reason why there isn't a Nobel Prize in mathematics. Because he was a brilliant mathematician that the math community said, oh, he's a mathematician from Norway? Those hicks. And they didn't recognize him until Abel was dead. And so Nobel said, fine. Well, if you don't care about Norwegians, you won't get my fancy-dancy award that I'm coming up with. So we came up with the Fields Medal instead. That's why there isn't a Nobel Prize in mathematics, but there is a Fields Medal, which is similar but different.
Did he come up with an award and present it to himself?
Nobel?
Yeah.
No, he just named it after himself.
He gave it to other people.
He gave it to other people. He named it after himself. It's like a foundation.
What about the field? Where did he get that?
I honestly don't know where the name came from that. Probably another person who had way too much money. So, if we have two things multiplied together, f of s and g of s, where big F of s is the Laplace transform of little f of t, and big G of s is the Laplace transform of little g of t. When we multiply the big f and g together, we get a new function, big h of s. We can find your little h of t by convolving the two. Notice we are multiplying little f and g of g and integrating them in this weird manner. T minus tau and tau, or tau and t minus tau. It doesn't matter which one you choose. They're the same. If you do a u substitution, it literally is the same thing. So always choose the where you put the t minus tau into the most opportune place. Yeah, so it's the integral 0 to t of f of t minus tau times g of tau d tau, or 0 to t f of tau g of t minus tau. Now, tau is just a dummy variable, so I could have done f of t minus smiley face g smiley face d smiley face, integrated from 0 to t. It's just a dummy variable that's hanging out there just long enough for me to integrate it out. Okay? So as I mentioned before, this is the same thing. I just need to do a u substitution. So if I set this equal to u, this ends up becoming u minus, or t minus u. That just wants to be triple. And as I mentioned earlier, this becomes a generalized or special product, and it's written as F asterisk G. I don't care which version of these you use. For some reason, analysts like this. By analysts, I mean people who study analysis, not data analysis. I tend to like the F asterisk G without the T floating around because it makes me think I'm multiplying by T, not that T is my variable that I'm plugging in.
Did you say F of T asterisk G of T?
So F of T asterisk G of T? Yeah. I've done that before. There's so many T's floating around though, it starts getting confusing too. So I usually drop the T's because it's assumed that F and G are functions of either T or X. So when you look in your text or look in other texts, you will notice that asterisk there haunting your very dreams. So, Laplace transform of this sucker. Okay? So notice we have a convolution that's occurring here. What's my f of t? What is my first function? T, right? I'm plugging in t minus tau in there, but this is just t. And my other function is? Sine of 2. Sine of 2t. So since my first one is f of t is equal to t, and my second one is g of t is equal to sine of 2t, I can do Laplace transforms of that. T becomes 1 over s squared. Sine of 2t becomes 2 over s squared plus 4. And once again, what is the Laplace transform of a convolution? Multiply them together. I believe the slideshow is already on Moodle too. So. If you want to find this later, it is on there. I think I put it up at 2 a.m. That was not a happy game. Okay. But most of the time, we don't start with the convolution and take the Laplace. We have the Laplace and we need the convolution, such as this. So, how could I break this up?
1 over s squared times 2 over s minus 2.
So we have a 1 over s squared as a function and 1 over s minus 2. Exactly right. I did it the opposite way. I put the 2 over the s squared, but it doesn't matter. The 2 is just going to be a constant here. But wait. There's more. Oh, great. Because remember, I'm not finding the Laplace transform inverse of this and then of this and multiplying them together. I have to do the convolution thereof. So,
what would be t minus tau e to the 2t minus tau?
Say that again?
Would that be 2t minus tau e to the 2t minus tau?
Easier than that. So it would be 2 times t minus tau e to the 2 tau. Only one of them is a t minus tau. But very close. Yeah, 2 t minus tau is nothing. I could do a simple, if that was the case, then I could do a simple u substitution. T minus tau disappears.
But usually the e, this one has the tau.
It depends.
Doesn't matter.
In this case, since I'm going to end up doing this, I see integration by parts. It looks like the t minus tau is the t function, 2t, is easier to get rid of easily enough. Whereas inside the exponential, it's going to be haunting my very existence.
Can you go back some?
Yeah.
That has been figured as 0 goes to tau and 0 goes to
T. 0 goes to t. Convolution goes from 0 up to t, because 0 is my starting point for the blocks, and t is my ending point, the number that I'm actually doing.
So tau is a number in the real space?
Tau is just a dummy variable, that's all. It's a holding position. I'm about to explain what tau means, but right now we're just playing with the formula. Give me a second and I'll explain.
I was also going to ask, what is, like, so those are your f of t and g of t, but how do you work that?
So we'd convolve them, right? We could calculate it out doing integration by parts. And this would be my final form. The convolution of t and e to the 2t can be easily calculated. But it really depends on the difficulty of the problem. It might have been easier to just write. In some cases, it will be easier to write just that. And it'll take a look at your directions of the problem. It'll tell you if you can get away with that. For example, do you want to convolve that?
God, no.
That's nice.
That's nice. You can't write it. Oh, no.
Let's do a reciprocal trig function. Let's not say we didn't.
Yeah.
Okay? Everybody got this that wants it? Okay? So rather than solve this right away, what does a convolution mean? So what's that tau kind of represent? Well, in this case, remember that my definition of my convolution is 0 to t, f of t minus tau, g of tau, d tau, right? But we've seen a similar form before, f of t minus a, right? What is happening to the function f? It's being shifted. So what's happening with this convolution? I'm taking this function f and I'm shifting it across my function, like so. And as I shift my function across, I'm taking the integral over that whole thing. It's sort of like, it's acting like a filter. I'm filtering out. Well, when I take my filter and I integrate across, and I integrate across, and I integrate across, what are the effects of my integral as I move it across the function? So the A is the area under our setup. So as I move this red square across, notice the area grows and grows, so my convolution grows and grows until it reaches its maximum here, and it decays down. So the convolution of my two squares is a pyramid, or a little triangle. So what is a convolution? It's a shift. It is a filter across both. As these two functions pass across each other, what is this area that exists between the two? And this is why convolutions are so hard. Because what the hell is that? Okay? It's weird. It can. It can. I haven't seen a lot of my fluids. I don't spend a lot of time in fluids. I spend most of my time in analysis. So I see a lot of this in analysis. I hate convolutions. But they're very, very powerful. They're very, very useful. Go away. And so the same thing can happen here. So notice in this case, as my square went across my jump up, my growth and decay, then it grows in size as I intersect more and more with the square, but then it starts to decay as it moves down because it's intersecting with less and less of the area.
So that you use these analysis for people who analyze.
Analysis is the proof of calculus. So, for example, let's let f of x be equal to 1 when x is a rational number, and 0 when x is an irrational number. What is the integral from 0 to 1 of f of x dx? Is this a continuous function? No freaking way. It's discontinuous at every single point. But I know what the integral is. Because of analysis. That's what analysis is. And so that's why I want to differentiate between data analysis, as you think about it, using when you might be dealing with any sorts of tabular formats and stuff, and then analysis in the math form, which is the proof-based stuff of calculus. And analysis in this case comes from by convolution, because a lot of calculus is the proof-based stuff behind different equations. Okay? So now you kind of have an intuition, just a smidge more than I was taught. My teacher said, here's the integral, have fun. And which means that I went looking for my own understanding of what a convolution is. But so we have that idea of what a convolution is. Let's solve an equation here. Okay? Y double prime plus 4y is equal to g of t, some g of t. I don't know what it is. I know I can take the Laplace transform of it, but that's all. With initial conditions 3 and negative 1. Everybody got it? Let's have fun. Take the Laplace transform of it. So y double prime becomes s squared y minus 3s plus 1, or minus a negative 1. I have no y prime, so 4y becomes 4y, big Y, and g of t becomes big G of s. Hoo-ha! Solving for big Y of s, I move all my non-big Y's to the right-hand side. So I get, and factor out, I get s squared plus 4 big Y is equal to 3s minus 1 plus g of s. As always, I'm going to divide by the s squared plus 4. This is easy, right? This looks like what? Cosine. This is almost sine. Sine of 2t, just like this is cosine of 2t, this is almost sine of 2t, so I need to do a little bit of maneuvering there. But this one, especially since I don't know what g of s is, move it out and I'm multiplying by my g of s, and this becomes sine of 2t. So I'm going to have 3 cosine of 2t minus 1/2 sine of 2t plus, what's that? Sine of 2t convolved with g of t.
Oh my god.
Here we go.
Here we go.
Now, do I know what g is? No. So what's my answer? That. But notice that now, regardless of my forcing term, if g is 0, then that term goes away. If g is my delta function, I can plug my delta function and let it go. Right? Oh, dear God, frozen. If it's my unit step function, I can do that as well. But that's what makes convolutions, as we mathematicians like to call it, power. That in this form, as long as g of t is integrable, I have my answer. G of t might not have a derivative. G of t might not be smooth. G of t might not be Riemann integrable. That means the integrals that we normally do in this class. But as long as I can use a mathematical technique to integrate this, g of t might be some set of data that your computer have registered. And using some MATLAB command, and you can involve the data points, I now have a numerical answer, where my analytical would leave me behind.
Would the volume constant be the same as just multiplying it, or?
Because remember, if I have some constant, 3, and I convolve it with, say, t, right? I could just 3 tau d tau from 0 to t, and this just becomes the simple integral. So I can totally convolve by a constant.
I was just curious if you can't like plug in a t minus tau or tau. So
Yeah.
How would you figure? Okay.
So we love constants because t minus tau goes bye-bye, and I just integrate the function.
Wouldn't the sine, if you sine stand so on the top?
Oh, remember I'm multiplying by g of s. I guess if I really wanted to, I could have also written this as 3 cosine of t plus, so if I move this in, so this is plus g of s minus 1 times 1/2 2 sine squared s squared over 4. So this could end up becoming g minus delta convolved with 1/2 sine of 2t. Because remember, delta of t, my delta of t when I take the Laplace of that is equal to 1. So I could have done that, or I can just do that. So I could have grouped them, or I could leave them alone. Okay? And so this ends up getting into this interesting kind of theory, and it allows us to start taking a look at, remember I've been putting that h of s there occasionally, right? That I'll have like e to the negative cs h of s, right? And we end up writing this, when we transform it into uc of t, h of t minus c. And you might have been, and some of you have asked me, What's h? Today we get to answer that question. And it comes from breaking my equation apart. Notice this first part depends solely on my conditions from earlier. Remember, this, my 3s minus 1 came from my initial conditions. And my s squared plus 4 came from my differential equation. So this first term, this first fraction, is totally dependent on the system. Whereas my second fraction, which I'll call psi of s, big capital psi of s, it's going to depend on my forcing term. And this allows us to really take a look at my h of s. And we'll be taking a close look at that because h of s is just 1 over s squared plus 4, right? And when I took the inverse Laplace transform of that, I ended up getting a little h of t, which was 1/2 sine of 2t. Remember, that showed up earlier as the thing I was convolving, right? 1/2 sine of 2t. And that's what your h of s is. It's the thing I convolve. And so because of that, it has its own name. H of s. Sometimes because it's transferring the information in real space from the differential equations into your answer. It is transferring. It's transforming. So your h of s is your transfer function. And it only depends on your system coefficients. It is transforming your derivatives into some answer. And the g of s is some external force. It's your forcing term. And so your h of s and your g of s, when multiplied together, start giving us a hint of what that transfer function is. Because when g of s, big G of s is equal to 1, and little g of t then is obviously delta of t, we end up noticing something very, very interesting. H of t is the answer to this problem. Y double prime plus 4y is equal to delta, or delta t, with 0 initial condition and 0 initial slope. H of t is the response of the system to the unit impulse as a forcing term. And because of that, we oftentimes call that little h of t that we solve for the impulse response. Mathematicians aren't the best namers, but they tend to be kind of literal. And because of that, we will frequently convolve your forcing term with your unit response, which is exactly what we did earlier, right? My h of t, which was 1/2 sine of 2t, I convolved with my g, whatever my forcing term is. So, in an arbitrary system with constants a, b, c being real numbers, and a general forcing term g of t, and a general initial position, and a general y prime, I take the Laplace transform, I plug it in, and I solve. I'm going to get my first fraction as being related to the system and the conditions, and then I'm going to have my unit response. Convolutions are mathematicians' way of saying, let's plug and chug, but at a higher level. I have some forcing term, convolvent. That's my answer. Some of you are writing randomly, so apply to it. Okay? And so because of that, we end up usually breaking our problems up into two separate problems. That first fraction, if you remember, depended only on my differential equation and my initial conditions. The second one solely depended on the forcing term and didn't care about my initial conditions. So the first one solves the homogeneous initial value problem. The second one solves the non-homogeneous initial value problem. And so we can solve these two problems separately, or you can break your differential equation apart into two separate problems, add the solutions together, and solve them problem one.
So it would be like y1 and y2.
Very similar to your y1 and y2. Not quite, but there's a lot of similarities. Think of phi, your phi of t here, being your c1y1 plus c2y2, and think of psi as being your particular solution. So complementary, particular.
Also, the first one should be any number for y or 0.
Any number you want.
For the second one, yeah, it's 0.
Mm-hmm.
So the homogeneous has to be 0 to complete the
Here? Well, because remember, your psi in this step, your psi was this one right here, right? So notice all the initial conditions are over here. None of them are over here. We just have the as squared plus bs plus c here. So this first one deals with initial values. This one doesn't. And so if I break my problem apart into capital P and capital psi and solve, that's why psi doesn't have any zeros, because in my answer it doesn't involve any initial values, whereas my phi does. That's why. And psi is just involved, as we talked about before, by just involving your unit response with your forcing term. Makes sense? I'm not saying it isn't easy. I'm saying does it make sense? I said today was going to be weird. Okay? This is convolutions. Right here.